You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcast. And I have Christopher Hendon, Assistant Professor in Computational Materials Chemistry, University of Oregon, Department of Chemistry and Biochemistry. He's also known in some circles as Dr. Coffee, because he's taken science and applied it to creating the perfect cup of coffee and looking at different coffees, which we may get into a little bit. But Chris, thanks for coming. How you doing?
Yeah, my pleasure. I'm going really well. It's a beautiful day here in Eugene.
Yeah, so tell me about your research work. What is it, besides the coffee stuff for a start?
Yeah, well, so I'm actually one of three new hires at the University of Oregon. The university put forward a series of cluster hires, and one of them was in energy storage and materials chemistry. And so I'm the first of three. We've also made two other hires. And I'm a theoretical chemist, which means that I use a computer to back out numbers, if you like, quantities associated with materials, whether it's their electrical transport or what color they're going to be, things that are important to energy storage. And so we use supercomputers, and I had a small research group here of 4 graduate students, and we're going after a variety of energy-related problems.
Oh, okay. So such as what kind of problems are you looking at? Like solar battery storage, or what kind of things?
Right. So one of the major problems that we're facing at the moment is we're actually very good at capturing light and turning it into electricity, but the issue is then storing it rather than using it on the spot. And so one of the technologies that is emerging is the idea of a supercapacitor, which essentially stores electrical charge in really high surface area electrodes. But the problem is there's not many high surface area electrodes that are really conductive. And so we're looking at a new class of materials that has extremely high surface areas and in principle can conduct electricity, but most of them do not. And so we're trying to elucidate the design principles that give rise to electrical conductivity in this new class of materials called metal organic frameworks.
So are you good at predicting materials? Like if I showed you a chemical formula, could you do certain math and prediction on what that molecule would do, what its properties were? Or is that still more of an emergent thing that's very difficult to figure out?
Yeah, so that's a good question, actually. When it comes to organic chemistry, if you think about a small organic molecule, this is pretty much the basis for the development of new drugs, drug discovery in the pharmaceutical industry. So it's actually a very difficult thing to do for a small organic molecule. At least it's bioactivity in any case. But we are very readily able to compute properties of that molecule, like, for example, its vibrational modes or its color or how stable it is, things that actually matter for other applications beyond pharmaceuticals. But if you were to show me a material that was made of other elements, for example, silicon and oxygen, much the same as silica, like what a window would be made of, it is actually a little bit easier then to predict its properties and its function, partially because you now essentially have a repeating unit. So this material is not behaving as a small molecule, but rather as a bulk material. But also because you've somewhat limited the problem to the function of the material as it exists when it's surrounded by, for example, air, rather than having to be chewed up by an enzyme in your body. So in general, my answer would be no, I couldn't tell you all the properties of any old scaffold that you showed me. But if you gave it to me in a different context, for example, here's a composition, that is indeed my job, is to try and tell you everything we could possibly learn about a material without actually having to make it.
Yeah, it's weird. I thought about this a little bit. If you have 2 different atoms, they're really only different in maybe the number of electrons and protons and neutrons, but they have all these emergent properties. The same thing with molecules. Where do these emergent properties come from? And, for your mathematical modeling, have you figured out formulas for color, formulas for reactivity? And does this tell you of any underlying structure?
Yeah, so it's interesting. So the last part of your question is if we have these formulas for color and reactivity and things, does that help us go backwards and start predicting structures? And that's a really difficult thing. Well, I'll tell you about a little bit more about that in a minute. We'll go back to the first part about these formulas that we use. So actually, most of chemistry is predicated on essentially the application of quantum mechanics. But one specific flavor has taken the forefront here because it's the idea of approximating a molecule by simply solving for where the electrons are in a probability function. In other words, you're saying, I can tell you everything about a molecule if I know the density of electrons. Now, why the density matters is because, of course, if you have a lot of electrons and they're all negatively charged, then they're going to repel one another, but also bind to one another in some way. And that results in differences in energies between these electrons when you compare two different compounds. And so that's why two compounds that could be very similar, for example, hydrogen chloride and hydrogen bromide, both of which are very similar acids, have vastly different properties. It's because the energy of those electrons is different. Now, the way we actually go about solving this is we take an embodiment of the density functional theory approach, which was proposed by a Nobel laureate, Walter Kohn, and his colleague Hohenberg. And essentially, we just solve their equations using some sort of cheating method to give us an approximation of where these electrons are. And once we've solved that, we pretty much know, more or less, almost everything about the system.
Well, when you say so hydrogen bromide, hydrogen chloride.
Yep.
What have you been able to model or predict about them? Their melting point, their freezing point, their reactivity. What kind of parameters are useful, and which ones can you figure out?
Sure. So if you want to model the melting point of a material, then you're going to need, first of all, the material to be either an amorphous blob of that stuff or a crystalline version of it. And then you're going to need to include temperature because, of course, you're going to try and melt it. Now, from a theoretical perspective, what temperature is just kinetic energy. So you're allowing the atoms to jiggle. And then if you do that, you then will probably also need to account for the fact that you're going to break a bond, the bond between hydrogen and, for example, chloride. So you're going to need to have some polarization and polarizability included, all of which is well described in quantum mechanics and density functional theory. And then you're just going to simply use temperature and sweep the temperature up until you have a sufficient amount of thermal energy to overcome the electronic energy that's keeping those atoms together. So that would give you the melting point. The color is, for example, purely related to what are the explicit energy levels of those electrons within one molecule, or perhaps how those electron energies changed if it was in a bulk material. But in short, the summary of that is that I have electrons in their ground state, and they're going to be at some low energy level. And the energy required to promote one electron from the ground state to the excited state gives us the color. So that's the idea of subtractive light. The color of that compound would appear to be all the colors that were not absorbed by that material. That's a particularly simple example. What's more related to what people are doing in my group and as well as in most research institutions is looking at additive coloring materials. In other words, light emitting diodes. So if I were to apply a sufficient amount of electricity to hop that electronic gap that I just told you about, what color would that gap correspond to? In other words, what color would the material emit? And so you'd be making LEDs essentially. And so people really care about that because what you're really doing is then having you're tuning a quantum level. So you have essentially control over a single electron's energy, giving rise to a macroscopic observable of color, for example. And so in principle, going back to your original question of what can we back out from these types of calculations, depending on how much you want to include in your model, you could back out everything from melting point, which I would say is sort of a macroscopic property of a material, all the way to its, some property arising from the quantized energies of electrons, which could be color or perhaps their vibrational modes or, rotational vibrational effects that you might see spectroscopically. And even things like tunneling energies to move an electron from one position to another position without having to go over an energetic barrier. These sorts of properties are.
Oh, really? Are tunneling energies quantized, just like electron energies?
Yeah, well, in principle they are. In practice, it's very difficult to measure. So what we typically would say is I take two materials, both of which have a ground state energies and quantized places where positions where I could put electrons. And then if I observe experimentally that I do see electron tunneling between species A and species B, with knowledge of what the electron energies were before the tunneling, we would then be able to make a statement about the energetic barrier for that tunneling. And so that would be where you'd back out the energies of those ground state orbitals, and then you'd essentially say, okay, the difference between those was the tunneling energy.
Well, is tunneling dependent on the context in which a molecule is sitting? If it's in a liquid, or if it's surrounded by a gas, or if it has certain conditions, pressure, temperature, etc. Does that change the tunneling energy or the likelihood?
Yeah, it does. Yes. So I'm not an expert in the field of quantum tunneling, but I can tell you that there is strong dependence on the energetics of the orbitals in which the electron is coming from and going to. And those are properties that are dependent on temperature, the electric field produced by their surroundings, and so forth.
So if you have a compound that's in a gaseous state, you can predict its melting temperature, etc. But can you predict the properties of it as a liquid versus a gas, or as a solid, or near absolute zero, or as a plasma? Are you able to extrapolate it that far?
Sure. Actually, the absolute zero is actually the easiest example for us to predict, because that's the temperature in which there's no kinetic energy included. And so most density functional theory and other techniques that people use to model the electronic structure are actually temperature independent. Now, you can include temperature, as I mentioned before, it's a function that essentially adds kinetic energy, if you like. But that's a sort of you're usually going after a different result. You're looking at, like you said, something like the melting point or whatever. But you actually also touched on one of the major problems in chemistry, is that we really do care about the electronic structure of things. For example, an enzyme, we want to know how it works. And it's solvated absolutely in water. But the difficulty is that we need to then somehow treat the enzyme with quantum mechanics, but we don't want to treat all of the water with quantum mechanics, because that would just be a tremendous computational expense. So actually modeling liquids is one of the vast challenges in essentially understanding chemical systems, whereas gas phase is quite straightforward in the sense that most of us would typically think of an ideal gas when we are modeling the gas phase, which is defined then as a gas that's not really interacting with anything else. So in other words, it's just a molecule in a box. And so that's an easier one to describe, because we make the approximation it's an ideal gas, and of course that falls apart for things that are not ideal. But that one's not so difficult. And then for the solid, that's actually very trivial. That's much the same as modeling the gas. If a material is solid, then it has a given density, and so I can construct a box and fill that box with whatever the composition was. And nominally, I could model that as either a crystalline material with repeating order within that box, or I could make a really large box and have pseudo disorder within that box. And so that would be the equivalent of an amorphous material.
So can't you take like an arbitrarily small, cube and model liquids using like a finite element analysis? If it's small enough, and you could see, with each water molecule, it only has a certain number of molecules adjacent to it. We can model that and then extrapolate outwards.
That's right. So you can do that. The problem is that local electronic and ordering effects are not necessarily as sort of long range as one might expect. So, if we look locally at any given water molecule, it's going to hydrogen bond to things, and you'd be able to describe that pretty well, but you would artificially be forcing that system to have that order periodically if you extrapolate it from a small box to a large box. Now, you may not be wrong, but it is absolutely entropically disfavored to do so, because that is inferring that there is that order periodically, which is a single point on otherwise more complicated potential energy surface. So that is one way that people do it, but there's problems with that.
And of the molecules you look at, I'm just curious. I would think that you've seen a lot of things that very few people have seen, coming out of these equations and these modeling. Like, for instance, if you look at organic molecules versus inorganic, do you notice a difference? Is there any fundamental difference, or it's just, a molecule is a molecule? There's no extra emergent behavior when you have organic molecules versus not?
Yeah, that's a really interesting question. So the thing about organic molecules is that if you look at a periodic table, most organic molecules are constructed from, let's say, the first 3 rows of the periodic table. You'll of course find some organic molecules that have selenium or iodine in them, but it's pretty rare. So in general, because those molecules are sitting relatively high up on that periodic table, then most of them have really relatively stable electrons. So in other words, they're pretty low energy electrons. And so the main differences between modeling organic compounds and inorganic compounds is typically the organic compounds are pretty stable. Of course, there's examples where they're vastly unstable. For example, if you have a really crazy bond angle, or you've deliberately made a really polarized bond or something like this. But in general, the main difference is that when you get down into the later elements in the periodic table, even as early as, for example, titanium, you start to get interesting properties that arise from titanium having electrons that can come and go from titanium relatively easily compared to that of carbon. The key thing, however, is that the field that sort of people typically either work in organic chemistry and they're making molecules and they perhaps have some organic semiconductor angle or a medicinal angle or something like this. And then the people working in inorganic chemistry are typically working towards some quantum data storage, for example, storing information in electron spin, or trying to capture energy or store energy. And it's at the interface between the two that things become kind of complicated, because essentially you're saying you've got low energy electrons on one side, and that's going to interface with the high energy electron of the metal, and you're hoping that they are going to have some interesting emergent property because of that. And indeed, that's an area that people have been working in for a long time, and that's the organometallic chemistry. And actually, that's given rise to most of the technologies that you think of on the industrial scale. So, for example, polymerizations that make low-density polyethylene and high-density polyethylene. Things like large-scale production of, essentially any polymer. I'd say that was a really good example of that. Is the chemistry that emerges from the interface.
And, I know there's probably a real simple question, but then again, it's just odd to me. Like, what is an electron bond? What is when 2 atoms bond? Literally, what's happening? I know they're sharing electrons, but what have you seen that's happening? Maybe on a deeper level. What else is going on? What makes a bond?
Yeah, what is a bond? That is the timeless question in quantum chemistry. So, everyone's got a different way of defining it, but from what I've seen, my definition of a bond would be if you have 2 species that contain electrons and you put them near each other and they become more energetically stable. In other words, you've essentially allowed those electrons to find a lower energy position, independent of whether they're in the same orbital. There's some quantum mechanical effect, like, for example, one is spinning up and one is spinning down and they form a covalent bond or whatever. I would call any energetic stabilization a bond of some sort. Now, then within that, there's a spectrum. And so from my side, when I run a calculation, I back out essentially what we're solving for is the exact energies of each electron. And so when we examine the electron energies of a system like, let's go back to hydrochloric acid again, HCl, you could think of modeling that as H in a box and Cl in a box, and then you put them near each other and see what happens to the electrons. And so indeed, they bond, they share with one another, they make this covalency. But what that actually looks like is a construction of, instead of orbitals associated with each atom, you get orbitals associated with the molecule, and they're more complicated. They're a linear combination, if you like. And so these sort of more macroscopic orbitals, molecular orbitals, are then able to hold 2 electrons each, and you end up seeing sort of more delocalized and more complicated electronic structure where electrons that were formerly part of chlorine now are partially located on hydrogen and vice versa. And what we're solving for is essentially what do those orbitals look like and where is the highest density for each one of these energy levels. And then it is that density plus that energy, it is the energy and the density, not physically added together, that give rise to all the chemical properties and reactivity of that given molecule. So that's what we're really solving for, is looking for the energetics, and we're also looking for the locality of those electrons.
Yeah, and this only, I mean, again, I only know the basics of chemistry, but it's only affecting the valence electrons. So chlorine, has a bunch of electrons and
Right.
lower energy orbitals. Are those affected when it bonds?
Yeah.
Or are they left alone and just the valence electrons are affected and make this new structure?
That's not a basic that's not a basic comment. Indeed, that's actually a sophisticated one. So the core electrons, the ones that we think of as non-bonding, we treat in most of our models as non-bonding as well. We essentially dismiss them from the valence, from the bonding interactions, and so forth. Now, certainly, there are examples where accounting for those core electrons really matters, and I'll talk about one of those in a minute. But you're right. In general, it is the valence electrons that do all the work. And the reason for that is that they're the highest energy electrons in the system. So they're most ready to come and go from an atom, if you like, to be oxidized or reduced. And then because of that, that's what gives rise to all the quantum chemical properties that you would observe. Now, an example of when you might need to actually include the core electrons is if you're trying to model and understand an experiment where you're exciting core electrons using some X-ray. So an example of this might be X-ray photoelectron spectroscopy, where essentially you use an X-ray to excite an electron from the core to one of the valence unoccupied shells. Now, if I were to try and model that, but I didn't include the core electrons, then obviously I'd have a problem.
What happens if you do such a thing? If you shoot high energy at a molecule, will it? I guess it won't always excite the valence electrons. It'll excite it could excite, depending on the energy, the wavelength. It could excite any of the electrons in any of the orbitals, right?
Right, exactly. So the technique that we were just referring to, this XPS approach, actually is really useful for quantifying whether you have different oxidation states of metals. If you think the classic example, Aaron Brockovich example with the chromium 6 versus chromium 3 or 2, you can imagine that if you have chromium 6, that is chromium that's missing 6 electrons. And so then if I were to shoot a X-ray at chromium and promote an electron from its from its core energy, so somewhere in the really stable electrons, out to its valence, well, there's less valence electrons out there now, so you're going to need less energy to put one of these core electrons into the valence. And so actually, if I were to then compare chromium 6 to chromium 3, you would imagine then that because chromium 3 has 3 extra electrons, you're going to need a bit more juice to get that core electron out to the valence. So that's the example you could think of using this technique to essentially probe oxidation state. It's not super useful for that. There's other techniques based on similar approach where you use X-rays, but also just like the nature of the metal itself. If I gave you a rock and you said, what's in this rock? Well, each element on the periodic table has different electron energies. So one could use an approach like this to probe what is in that rock.
Well, what happens when you shoot energy at a molecule? It would probably, it would affect a core electron. It would kick it up to a valence energy. Would it kick out one of the valence electrons then? Or what happens to it?
So it depends on if there's low energy electrons or low energy unoccupied orbitals that this core electron could go into. But for a lot of molecules, it's easier to ionize them than it is to excite them. So in other words, what I'm saying is if you shine really high energy photons of some sort on a molecule, there's a good chance you're just going to shoot an electron off of that molecule, and the molecule will then be relatively positively charged. Now, it may be super unstable, but essentially that is one outcome that could happen. And another outcome, of course, could be some excitation. What determines whether it's going to be ionized or simply excited is the energy of the unoccupied position in which that electron would end up residing in, at least transiently. And so a lot of molecules, that next unoccupied orbital lies higher in energy than the so-called vacuum level, which is the energy required to remove an electron from the molecule entirely.
So if you're removing a ground state electron, one of the higher energy electrons will then fall, will emit energy and fall down to cover that ground state electron that was lost?
Exactly.
Okay. You'll never have a hole, and it'll never stay like that. It'll always fill in the lowest energy level first.
Right. You can think of it, like everything trickles down if you want to think of it that way.
Interesting. Okay. Any, I guess in your work, this is kind of a general question, but what surprises have you gotten from elucidating the structure of electron clouds and, and molecules bonding and interacting? What things have you seen that you thought are really surprising or unusual?
So most of the surprises and the peculiarities that I come across are actually in the organic chemistry field rather than in the materials field. And that's not because materials are all known and everything's solved, but it's because I'm just more fascinated by small organic molecules and how something so small could have such a dramatic impact, in your body or in your life and so forth. And so there's a few crazy examples I really like. For example, as you mentioned before, I'm also work in coffee, but more generally in flavor chemistry. And I find the idea of having a difficulty predicting flavor or smell of a compound is extremely curious, given we know everything about that compound, its vibrational modes, its melting points, all the possible things you can imagine, its stability and so forth. Yet we still have trouble predicting what the molecule would smell like. So, that's something that my group's been working on for quite some time now, is trying to understand how we could predict smells, and that's really difficult. And so that's always been a fascination. A recent topic we've been thinking about is the anti-cancer drugs based on platinum, how those particular compounds actually function, and how certain platinum compounds have a higher affinity for one cancer rather than another one. Those minor differences based on small structural perturbations are very surprising to me. But perhaps that's because I'm not an expert, of course, in biology. Maybe this is obvious to a biologist, but to a quantum chemist like myself, I find these minor perturbations very intriguing.
Yeah, well, I highly doubt that biologists would know, but interesting. Based on what you know about quantum chemistry, I recently read that scientists are starting to see a lot more quantum effects in biology.
Oh yeah.
I don't know if you're aware of any of this, but does that make sense to you based on the angle you're coming from, that this would be possible in a living creature?
Oh, absolutely.
Any quantum effects as tunneling, coherence, etc.
Sure. So several Nobel Prizes have been awarded for various different spectroscopic approaches to probing quantum effects in biology. Those ones are, have obvious utility. Imagine if you are incorporating a dye into the human body and you want to observe whether this dye has been uptaken into a particular cell, but you're looking for something very, very small, then you're going to need to have some sort of spectroscopy. The one that was really popular was confocal spectroscopy, which allowed you to essentially take an image with some sort of fancy microscope and determine where molecules were in particular cells or other matrices. That is extremely interesting. Myself, I've actually worked in a quantum phenomenon that occurs in biology, which is this idea of transferring a single electron through a protein. And the example was that there's essentially a series of enzymes, the monoamine oxidase enzymes. One of them they're responsible for chewing up serotonin and so forth. Essentially, without these things, a lot of biological functions that make you happy and feel things are diminished. In any case, there was a wonderful study on the function of one of these enzymes where I guess some chemical biologists were able to substitute one of the amino acids on the periphery that had been known to oxidize in certain media, and the whole enzyme ceased to function. Now, typically, a biologist would invoke that caused a structural change and the active site was no longer intact and so forth, but one way or another, it seems to be that the active site is intact, and actually the reason for that enzyme not functioning anymore is that particular cysteine motif that contained a sulfur was no longer ionizable, and because it's not ionizable, it was unable to relay that hole, the omission of an electron, into the center of the active site, and therefore the function of the enzyme was dramatically decreased. So we went through and computed the essentially redox potential of that protein and demonstrated that was probably a likely outcome, or the likely cause of this was the lack of the sulfur. And there seems to be growing evidence that actually these sorts of electron relays in your body play a major role in enzyme function and so forth.
That's amazing, yeah.
But quantum effects. Just sorry to interrupt you. Quantum effects. Just thinking about the general term quantum effects is an interesting one because essentially, when we think of, as a chemist, everything in our vision is quantized. We typically think of molecules moving around in a body as a Newtonian effect because it's an object with mass and it moves with temperature and so forth. But actually, all of the properties that give rise to or that come from that molecule are all quantized. A great example of this is, asphyxiation with carbon monoxide occurs because it binds almost irreversibly to the iron site in heme. And so in that case, you would say that is quantized because the energy of that binding is well described. And so, if you want to think of it that way, then pretty much everything in your body could be quantized. The problem is just trying to put a number on something that's so macroscopic can be sometimes convoluted.
Like even if everything's quantized, all the possible states of all the possible molecules and atoms and systems, you could have infinite number of things, of states, yet still be quantized.
Oh, absolutely.
Very interesting. Would you mind if I ask you a little bit about your coffee work?
Sure, go ahead.
Yeah, if you don't mind, just tell me and listeners what makes you so interested in coffee and what kind of interesting things you found out about it.
Well, the United States, obviously, I work in the United States. So when I think of pitching an academic motivation, I usually use the American market, but certainly coffee is widely consumed worldwide. So take what I'm about to say and more broadly think of this in the world context rather than the U.S. context. But the coffee industry is worth a tremendous amount of money. So in the United States, it's worth about 1.5% of the GDP, which equates to roughly $225 billion a year. And that's including, import, export, retail, cups, et cetera, all these things. So with that in mind, I would say that is a pretty valuable industry. And certainly compared to other industries that I work in my, day-to-day job, it rivals them, if not trumps most of them. So with that considered, we have this extremely valuable product that we work with day to day. And in fact, pretty much everybody on earth is aware of coffee's existence. So it's an amazingly ubiquitous material. Yet there's tremendous variability in the enjoyment of the beverage, as well as just more on the physical and chemistry side, what the beverage actually is and how it came to be. And so with that in mind, I was essentially fed up with variability in coffee. And so that's why I've taken a more academic approach, is to try and figure out how we can reduce the critical variables in the coffee production. But also, I initially became interested in it because something as simple as water chemistry plays a tremendous role in the flavor and perception of coffee. And a high quality coffee could be perceived as very low quality and vice versa, depending on the water chemistry. And so, that was my intro to it, and that got me excited about the application of science to coffee. And then, things have grown from there.
Has anyone created something you could drink that would counteract caffeine? If I want to drink a coffee at midnight and then go to sleep 2 hours later, has anyone figured out what I can drink to shut down the caffeine? Because it has such a long, I've heard it has like a 6-hour half-life. I just wonder if there's a compound that counteracts it.
Yeah, that's a good question. I don't know if there's a compound that directly counteracts caffeine. Anecdotally, I know that essentially people who drink coffee late at night and then drink beer immediately after seem to find that they can sleep. So perhaps it's just any downer, if you like, that might counteract the sort of the upper effect, if you like, of the caffeine. But
have you studied how caffeine is utilized in the body, or have you studied more the chemistry of brewing the coffee and its impact on your sensory experience of it?
So less on the sensory experience and none on the biology once the coffee has been brewed. In fact, I'm far more interested in the production side. In other words, like anything from when the coffee was being grown as a plant all the way to the point in which it becomes, mass solvated in water. After that, of course, you enjoying it is a critical part of the coffee experience, but I'm not trying to homogenize flavor. In fact, I'm trying to embrace it. I just want to ensure that the barista, the person who's preparing you the coffee, or perhaps you preparing it yourself, is able to do it reproducibly and obtain flavors that they are looking for without having the variability of things like water chemistry or your grinder misbehaving or other things.
How good are you at making it? I mean, do you have like coffee companies contacting you, or at least friends and relatives begging you to make them coffee?
Yes. So I work actively with many coffee. In terms of making coffee, when you get to a super technical level, you'd be amazed at how most people would actually prefer to consume coffee. First of all, the first thing that happens is most of us don't like actually making coffee ourselves. And most of us would rather go to a cafe and embrace a bad cup of coffee at a local cafe, or perhaps a good one, whatever, than make it yourself. But if we were tasked with making coffee ourselves, most of us have found a really simple way to access a flavor profile that just is really enjoyable consistently. So, for example, in my office sitting next to me right now, I have a burr grinder that I believe produces sufficient grind quality. The water that I use, I live in Eugene, so we have soft water, and that's good enough for me, even though I wrote a whole book on how soft water is not ideal. But it's good enough for day to day. And I get given coffee from people all over the world that are far too generous. And I present these coffees to all my graduate students, and we sit around and we drink it and talk science. So, most of us are not really once you get to the level where you know a lot about it, you actually end up taking a step back and saying, whatever, it's coffee, it's fun. I don't know if you've ever interviewed somebody who works at like UC Davis in the wine department or whatever, but in viticulture and enology, they don't necessarily drink, $600 bottles of wine every day. And it's much the same for us.
Well, can you take what would normally be thought of as junk and make an amazing cup of coffee with it by using different methods?
So then there's a graph that I've constructed and typically would show at this point, which essentially says that 50% of the cup quality comes from the green agricultural products quality in the first place. Then the remaining 50% is subdivided into macroscopically 20% being related to the roast, 20% being related to the water chemistry, and only 10% related to the brewing apparatus. If you mess up any of those, of course, you mess the cup up. But the point is that if you were to just give me a piece of junk, there's only so much that I could do. I could only make it 10% better than you could. But if I got to present you with any coffee that I would like in the world, I am certain that I could get, significantly better than a piece of junk coffee.
So is there much modulation by the time you're at a coffee shop? Is it true that, Joe, your favorite barista, really does make it better than Mary? Or is there just a slight difference there to be had?
Yeah, so that's an interesting question. So when I ask the scientific community what they think the greatest variable is in the production of coffee in a shop and why we see irreproducibility, scientists will never point towards the human, because scientists are actually, I think it's quite a positive outlook on life. We all think that all humans are equally capable of performing the science, and that it's probably some variable that is sort of either undercover or wasn't controlled for, but it wasn't really the human's fault. So in your example, I would say that neither of the baristas are to blame. It's that rather one is doing something that the other one is not, but it's not the human that's messing it up. It's just that, for example, one might be using a little less coffee in their production of the coffee, and that's giving rise to a different flavor profile that doesn't necessarily suit you as the consumer, but maybe suits the barista who served it to you. And so there's a lot of variables, but most of us would typically not attribute the variability in coffee to the barista.
Well, I've noticed there definitely is a big difference. Like for instance, if my wife's going to cook dinner and she's mad at me, the dinner does not come out good. So it does seem like the person that's making the drink or the food, depending on their mood and who they are. I mean, just some people I've noticed just make amazing coffee, and some people it's terrible. And I don't know what they're doing differently, but
right.
They're pulling the shots longer or
right.
So it's weird.
Yeah, so I can actually speak to that. So I can't speak to your wife making you variable dinners, but I can speak to you to the variations that could arise, that could give rise to one barista, for example, being slightly different to another barista. So some variables that are more tangible are, let's imagine that we're talking about espresso here, because that's one that's at least one component of it is powered by a machine. But in espresso, the mass of coffee that you put into the filtration apparatus, the basket as it's called in the industry, that mass is important. So let's say somebody puts 20 grams and someone puts 19, those coffees are going to be vastly different. Then the mass of water that is pushed through that puck and then giving us a resultant beverage of some arbitrary volume, that number needs to be controlled for as well. Now, some people will do that by eye. Some people will do that by, measuring it with a scale of some sort. But in circumstances where people think that one barista does something better than another one, it's usually just that the barista is either being way more reproducible, in other words, they're doing the same thing every time, or that they are really doing a different recipe entirely. So, for example, they put in 20 grams into the basket instead of 19, and they're pulling 40 grams out instead of 50. So, in that particular example, the person who's putting 20 in and getting 40 out is going to have relatively higher concentration, and it's going to taste more acidic and less over-extracted. And the people who are putting in 19 and pulling 50 out are going to be running more water through, so they're going to be extracting more stuff that might taste bitter, for example. So those are the sorts of variables that give rise to what humans perceive, consumers perceive as variability between baristas. I'm not so interested actually in the variability between a barista. I'm more interested in the variability for a given barista, right? I'm trying to say, let's let a barista make a decision about a flavor, but I want them to be able to hit that exact same flavor twice. What do they have to do?
Well, it seems like that's partially accounted for. When I go to coffee shops, they have the big coffee machines and they just kind of push a button. So you think the shot pull time is the same, and they have, scales where they weigh the coffee and take off a little bit so the amount that goes into it's the same. I mean, it looks like they're trying to control a lot of those variables pretty carefully.
Right. Yeah. Right. So it turns out that actually, even when you do all that, there's still other variables that are just simply not accounted for. For example, in the espresso production, when you put all those fine little particulates into that basket and pack it down, water will not flow homogeneously through that puck. And it is somewhat random as to whether you're going to have regions of really high density or a homogeneously distributed puck that has, little pieces decorated evenly throughout the whole puck. Now, on average, sure, it's going to be random, but for a small sample size, between let's say 10 shots, one might very well be essentially a bad shot. And so the question is, how do we minimize that variation?
I guess you could create pucks with different geometries and flow characteristics and heights and inner baffles to make sure the water flows the right way. I'm sure people are working on that kind of stuff, right?
Right. So a lot of work's been done on that in the sort of machine side. Typically that sort of thing is you see incremental advances in that front, and you'd be amazed, but actually things as simple as trying to isolate how a grinder produces the dust that it produces is still an empirical art. In other words, if I wanted to make a systematic modification to a grinder so that it made a different particle size distribution, that is not something that you can just readily do. You have to try hundreds of different burr designs to get that to work. And so there's a lot of fundamental advances that still could be made. But having said all of that, all of these are on the consumer side, and they're the really low-hanging fruit problems that we go after. But there is much larger problems in the coffee industry. For example, how do I consistently grow a higher quality crop as judged by this particular score sheet? What gives rise to variability in that crop, and so forth. And that's really what we're trying to understand is, we're using the brew side to essentially say, how can we homogenize extractions for a given crop? But what would be more valuable, of course, is how can we then begin to predict what the next crop is going to taste like, or what we need to do to be able to obtain, a desired profile from that coffee.
What kind of variations happen in crops that cause different flavors?
On much the same as wine, on dry and hot years, that you'll see variability between different crops. And you could also imagine that you have, bugs or other insects and funguses and that sort of thing that could cut through your entire crop in a year. There's not really, in most coffee producing countries, there's not really fertilizers available. There's not sophisticated or precision agriculture. These are typically relatively poor countries, and coffee is primarily one of their major exports. And for example, in Burundi, coffee is 25% of the GDP and 90% of the employment for the country. So, most of the time it's just kind of like whatever nature is giving us is what we're going to end up with. But the question is, okay, well, if that's true, is there something that we could do as scientists that could, for a very low barrier to activation, to actually get this to happen? So not a huge cost investment. Could we revolutionize the production methods somehow such that, the farmer saves money or their crop becomes systematically increasing in quality or something like this? And so that's really what we're looking at.
Is there, the best coffee in the world in your opinion? Or are there ones that are just so dramatically unusual or delicious that you have to mention them?
Yeah, so every year, the best coffee in the world changes because it's determined by this score sheet that we use to quantify how good a particular coffee is. The score sheet is a multiplier score sheet, so in certain things are weighted very heavily, like perceived acidity, body, mouthfeel, that sort of stuff. And so, each year a new coffee is the reigning champion. And there's coffees that have won, or it's not a competition. There's coffees that have been scored highly, and number one even multiple times. It's much easier to say which coffees score low than it is to say which coffees score high, because of course the highest performing ones alter. But the lowest performing ones are ones that don't score well on the score sheet, and those are the ones that don't have really high perceived acidity, because that is one of the panels that we've decided is valuable in coffee. And so certain countries and producing regions typically score low, and those include Vietnam, Sumatra, Brazil, and Hawaii. And there's a few others as well, but those are the main ones. Now, that's not saying that they're low quality coffee. In fact, they could be extremely high quality. It just means that they score low on the score sheet. And so with that in mind, I would say that those are the ones typically that people would associate with low quality specialty coffees. And the higher quality ones have extremely high acidity, things from Ethiopia, Panama, etc. Having said that, when you think of coffee, and perhaps your listener group here would think of coffee, they are probably leaning towards thinking of companies like Peet's or Starbucks or whatever, your commercial grade coffees.
Yeah.
And, Starbucks has a branch of specialty coffee, for example, called Starbucks Reserve. And Peet's is known to buy specialty coffee as well. But the definition of specialty coffee is a coffee that scores above 80 on this score sheet. Now, anything that scores below 80 on the score sheet doesn't mean it's bad. It just means it didn't score good on the score sheet again. But it also does mean that if it scores below 80, it falls into the commodity grade, which means that you're not going to pay very much money for it. Now, perhaps it's a circular argument, but the point is that if it doesn't score above 80, there's a reason for that. It doesn't really possess a lot of those flavors that we're looking for. Or perhaps they do, but there's also too much variability. So if I taste 5 coffees of the exact same bag, I might taste defects in one of the cups or something like this. Now, those coffees are typically bought by larger companies because they cost less money. You roast them dark, you hide a lot of the imperfections. And, that's what the consumer these days relates to as coffee, is this sort of pretty dark roasted beverage. And you think of the more commercial places that would sell that sort of thing. But in general, those are relatively low quality coffees, and those companies often have a much higher quality coffee, but they're also worth a lot more money.
Can you rescue a low quality crop with good roasting and good preparation?
Yeah. So if your low quality crop is 50% of your 50% of your outcome of having an excellent cup of coffee, and you've already shaved that in half because you really have a pretty low quality crop, you're going to have to be a really good roaster. You're going to have to use perfect water, by which that would be the same water that the roaster used to quality control. And then you're going to have to brew this in a way that really only manages to pull out excellent flavors in that coffee, which is, honestly, it's possible. It's going to be tough.
Okay. Well, very good. Well, we covered a range of unusual subjects. At this point, I just want to give listeners some references. So where can they go to learn more about the coffee side of you and then the quantum chemistry side of you?
Sure. So most of the coffee stuff is pretty well publicized on various websites. Perhaps the things that are really interesting are I curate a folder of publications, peer-reviewed publications that are related to coffee research, and they can be found on my website. There's hundreds in there, and don't be scared by them. Just have a flick through them. If one interests you, have a read. And if you want to learn more about it, perhaps send me an email. I'd love to talk about it. In terms of my energy storage work, that has not received as much public notoriety. For example, you won't be able to read an article in the Atlantic about our computational efforts on developing new supercapacitor electrodes. But all of my peer-reviewed publications on that topic are also hosted free of charge for reading of it for anybody on my website. And I would also encourage you to, if you get excited about one of the particular topics that you see that we've studied, to also, look up on Google Scholar to see who else is working in that field, because I assure you, I'm one of many hundreds of researchers who are actively pursuing this idea of a greener energy storage solution. So, this is an active field, and it's a fun one to work in. And I will happily answer any questions that any of your listeners have.
That's great, Chris. Well, I appreciate you coming on the podcast. Thank you.
Yeah, my pleasure.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.